Hey everyone, and welcome. Have you ever thought about what happens when you take simple instructions, simple processes, and chain them together to build something way more powerful? Well, that's exactly what we're diving into today. It's a really cool mathematical idea called function composition. Let's get right to it.
So, think about it. You could take the steps in a recipe, or maybe lines of code in a program, and what if you could just link them end to end? You'd create a totally new, much more complex process out of those simple building blocks. And that, right there, is the big idea we're going to unpack today, but with functions.
Okay, to really wrap our heads around this, let's step away from all the abstract math for a second. We're going to think about something way more tangible, like a factory. Yeah, a factory. Let's actually build ourselves a function assembly line.
See, at its core, every single function you've ever come across is kind of like a simple machine. It's designed to do one very specific job, and that's it.
And it's always this three-step dance, right? First, you've got your raw material. That's your input, your X, that goes in one end. Then the machine does its thing, it processes it, and finally, out the other side comes a finished part. That's your output. Super simple, right? Input, process, output. Now, one machine by itself, super useful. But the real power, the real magic of a factory is the assembly line, right? It's when we start connecting these things together that things get interesting. So how exactly do we do that? And here's the secret sauce. The finished part that comes out of that first machine, it doesn't just sit there. Nope. It immediately gets fed into the next machine on the line as its brand new raw material. It's this perfect, seamless handoff from one stage to the next. So this whole process has a fancy name, of course. It's called function composition. And the notation, looks a little weird at first, that F with a little circle G, but it actually describes our assembly line perfectly. The trick is you read it from the inside out. You take your input, X, you run it through machine G first, and then you take that entire result and run it through machine F. And this is such a key idea to get. When you see F of G of X, you're not just plugging in a number. You're plugging in an entire process. You are literally embedding the whole G machine, its entire set of instructions, right inside the F machine. Okay, so having two separate machines is cool and all, but it's not super efficient, is it? I mean, what if we could just combine them? What if we could build a single advanced super machine that does both jobs at once? Well, we can, and we do it by finding a brand new formula. All right, let's see how this works with a couple of our factory machines. So we've got machine G. Its job is super simple. It just adds 1 to whatever you give it. And then we've got machine F, which squares its input. These are our two building blocks. So to build our new super machine, F of G of X, we start with a blueprint for the outer machine, F. And its rule is just something squared. Now, what is that something? Well, it's the entire inner machine, G, and its rule is X plus 1. So we literally just substitute X plus 1 into those parentheses. When we expand that out, FOIL it, we get our awesome, new, all-in-one formula, X squared plus 2X plus 1. So we've got the blueprint for our shiny new super machine. But does it actually work? I mean, we gotta be sure. We need to write a little quality control test to make absolutely certain it gives us the same result as our old two-step assembly line. All right, for our QC test, let's grab a specific piece of raw material. We're going to send the number 3 down the line and see what happens. Okay, method 1, the super machine. We take our new formula and we plug 3 right into it. That gives us 3 squared, which is 9, plus 2 times 3, which is 6, plus 1, and 9 plus 6 plus 1, that's 16. Okay, 16 is our benchmark. Now for the old school assembly line. First, we put 3 into machine G. 3 plus 1 gives us 4. That 4 immediately gets passed to machine F. What's 4 squared? It's 16. The final output is 16. Look at that. It matches perfectly. Our super machine is a total success. But wait a second. This brings up a really, really important question. And honestly, it's a super common trap. We just built F of G of X. What do you think would happen if we wired the machines up the other way around, like G of F of X? Would we get the same thing? Let's find out. Let's test it with our input of 3 again, but this time, reverse the order. Okay, so 3 goes into machine F first. 3 squared is 9. That 9 then goes into machine G. 9 plus 1 is 10. The result is 10. Whoa, That is completely different from the 16 we got before. So here's the huge takeaway. In function composition, order matters. And I mean, it matters a lot.
All right, just like any real factory, our assembly line has to have some really important safety rules. You can't just throw any old raw material in there, right? Some inputs can literally break the machines. In math, we call this set of safe inputs the domain. I mean, think about it. Some numbers are just going to cause an error, like trying to divide by 0 or taking the square root of a negative number. Our job as the factory manager is to figure out which starting materials are actually safe to use. And it turns out there are two main safety checkpoints that every input has to pass. Rule number 1, the initial input, X, has to be safe for the very first machine it enters. Makes sense. But rule number 2, and this is the one people forget, is that the output from that first machine has to be a safe input for the second machine. It's got to pass both checks to be allowed on the line. Let's look at this in action. Let's say machine F takes the square root and machine G just subtracts 5. Okay, if we start with an input of 10, well, 10 minus 5 is 5. Can we take the square root of 5? Yep, so 10 is safe. What about 5? 5 minus 5 is 0. Can we take the square root of 0? Absolutely. Safe. But look what happens with 4. 4 minus 5 is -1. When that -1 gets to machine F, the line grinds to a halt. It's trying to calculate the square root of -1, and that just breaks the machine in the real number system. So 4 is an unsafe input for this specific assembly line. So that's really all the domain is. It's just the complete list of all the safe, raw materials you can start with, the ones that are guaranteed not to cause a jam or break the line at any point in the process. All right, so let's do a quick recap of everything we've built today. We've figured out that functions can be linked together just like machines on an assembly line. We learned this process is called composition. We proved, and this is a big one, that the order of the functions dramatically changes the result. And finally, we saw that the domain is really just a set of safety rules to make sure the whole process runs smoothly. You know, this idea of chaining processes together goes so far beyond just math class. It's fundamental to computer programming, scientific models, heck, even your daily routines. So I'm going to leave you with this question. Now that you know how to do this, what super machines can you imagine building in the real world? What simple steps could you combine to create something new and powerful? Thanks so much for joining me.